Okay, in the last unit we were talking about estimating using boxes to help approximate the area under the curve. And we're going to look at another way to approximate a definite integral. Finding the area under the curve, and the way that we're going to do it today is by slicing a region into several rectangular strips, and then we're going to calculate the area of each of those strips and add them all up, and that's going to be an approximation. The idea when we first start off is that we're going to partition the entire interval into basically sub-intervals. So the first thing that we're going to do, and just for this example, I'm just going to put a couple little slices in here. Notice that I'm purposely making them at different widths. I don't want the widths to be the same because we want to generalize this. So we're going to make vertical rectangles that go all the way up to the height of the function. These strips that we're going to make are going to partition the interval from A to B. Into n sub-intervals. And n just talks about how many intervals you are going to make. In this particular diagram, I made 4 sub-intervals. So in this case, n would equal 4. And that's my microwave beeping. Yay! All right, we're going to choose values of x at sample points within each sub-interval. And just like the sub-intervals could be of varying width, your x location can be at varying places within the sub-interval. So let's say I pick this little guy, and he's going to be my first location. We call it C, and it's subscripted 1 because that x location is within the first sub-interval. We're going to, I don't know, let's pick over here. I'm picking arbitrary places again. So this is going to be C2, and this one let's do right in the middle. We'll call that C3. That's the third sub-interval. And let's do this one really close to the left of that interval, and we'll call him C4. All right, so within that first sub-interval, C1 is my sample x coordinate, and we're going to create a rectangle that goes all the way up to the function. So this is going to be f of C1, which would be right about here. And we're going to create the height of that rectangle using that function value. And we'll pretend that that's a vertical line. We're going to do the same thing at C2. We're going to go up to the function from that x coordinate, and that will create the next rectangle. At C3, that will go about like that. And then at C4, I chose a value that was very close to the subinterval x on the left. Now, obviously, you might ask yourself, why are you choosing those particular C values? And the answer is it won't matter in the end, and we're going to explain why in just a little bit. So for right now, they're arbitrary. If you take a look at the first rectangle, I could calculate the area of that rectangle by doing the base, which would be the width here. So this would be what we call delta x1. That is talking about the width of the first rectangle. And likewise, this would be delta x2, etc., etc., delta x3, and delta x4. Okay, so for the first rectangle, we would do delta x1 times f of c1. And that would give you the height of the first rectangle times the width, which is delta x1. That gives you the area. If you do that for all of them, and I'm not going to write it in, you would have each individual rectangle area. And this is where we get to this fun-looking little formula down at the bottom. And it says that the area of the entire, or the area of each individual rectangle is just f of ck, so that's the y value, times delta x sub k. And again, k is just where you are, which subinterval, all the way up to the number of intervals that you've chosen. And the beauty of this thing is if you add all of them up together, that's going to give you an estimate for the area under the curve. This whole process of finding the definite integral this way by approximating the sum of these rectangles is credited to Bernard Riemann, or G.F. Bernard Riemann if you want to get technical. So we call this a Riemann sum. And you will notice the exact same formula here as what we described up here. That's the area of each individual rectangle. And Riemann said if you add them all up, there's where the sigma comes from, that this is going to give you what the Riemann sum, okay, the approximation for the area under the curve. All right, there's three types of Riemann sums that we're going to talk about in this unit. The first one is considered an upper Riemann sum because in each subinterval you are going to take the largest function value for the rectangle's height. This is going to be an overestimate of the true area. Let's go ahead and just make 3 subintervals in each of the diagrams. And we're going to use this pen. Again, it doesn't matter where you draw the subintervals. We'll get to that later. So 2 tick marks would break it up into 3 subintervals. So let's take a look at this first diagram. Within the first subinterval, now you're only looking at the y values. Okay, so an upper Riemann sum is going to take the biggest y value within that subinterval, which would be for this subinterval at the right endpoint of it, and that is going to create that rectangle right there. For the second subinterval, you're estimating, eyeball it, it looks like it might be right about there. And for the third subinterval, that's definitely at the left endpoint of the subinterval. So you see how each of those rectangles has a little bit of the rectangle above the curve. So if we were to find the area, that's why it's an overestimate. So hit pause right now and go ahead and just sketch what the upper Riemann sum would be for each of the following 2 graphs. And then come back. Okay. All right, how'd you do? Let's take a look at the second graph. For each of the y values, they're all at the right endpoint of the subintervals. So, excuse me. So for this subinterval, if you take the rightmost endpoint, that's the highest y value in the region. And that's true for all of them. And then for the third graph, the first subinterval, it looks like the right endpoint has the highest y value. For the second subinterval, it's just before the right endpoint. That would give you the highest y value. And then in this last subinterval, it's the left endpoint that's going to give you the highest y value. But either way, we're just trying to pick the y value in each subinterval that's going to be the biggest, because this is going to be an overestimate. The symbol u sub n is used for the notation of these guys. So in your first diagram, you would say that u sub 3 equals, and then whatever you get for the area. So all of them, because I use 3 subintervals, would be u sub 3 upper. Okay? So as you can imagine, now we're going to talk about a lower Riemann sum. And that is exactly what it sounds like. You're going to take the smallest y value in each subinterval. And these are obviously going to be underestimates of the area. So in each of the subintervals, just pick the y value that you think is the smallest of all of them. And again, we'll go ahead and partition this. I don't know, this time let's be crazy. Let's choose 4 subintervals. And it doesn't matter where you make them. Doesn't matter if they're the same or if they're different. So 3 tick marks is going to make 4 subintervals. So all of these would be L4s. Okay, and again, I don't have any actual numbers on here, so we can't find the actual area of these rectangles, but we're just trying to get an idea. I'm only going to do the first graph, and for this one, it would be the left. Whoa! It would be the left endpoints of each of these subinterval. Of the first 2. In the third subinterval, I don't know. Eyeball it. Looks like again it might be the left endpoint. And for the fourth subinterval, you're going to choose the right endpoint because that's the lowest y value. Okay, so you see how there's kind of a little bit of space between the top of the rectangle and the function itself. So if you were to, this would be missing area that isn't accounted for. So that's why it's an underestimate. Okay, so you've got an upper sum, which takes the biggest y value. You've got a lower sum, which takes the lowest y value. And as you can imagine, the the best representation for an estimate of the area would be to do a midpoint Riemann sum. And it's a better approximation to the true area. This is worthy of highlighting and noting that a midpoint is not averaging the upper and the lower, okay, because it's talking about taking the function value at the midpoint in each subinterval. So it has nothing to do with the actual y values. You're only taking into account where the x is located. Here's what I mean. Let's do 3 subintervals to make this easy, and I'll go ahead and show you for all of them. And then I'm going to go ahead and use red to indicate the midpoints. So if you take a look, here would be the midpoint for, here would be the midpoint for the first subinterval. Here's the midpoint on the second, and here's the midpoint on the third. You're using the y values at those midpoints. So that would be about here for the height. That would be about here for the height. And that would be about here for the height. Okay? So the thing that I'm going to point out with this is, let's just take a look at the first subinterval. You've got a little bit of the rectangle that is over the top of the function, this guy right here. But then you've got a portion of the function that isn't represented by the rectangle that's being shown. So there's an overestimate on the left part of the rectangle, but an underestimate on the right part of that rectangle, which means it's going to be a pretty accurate description for the area of that under the curve. So again, I could show you on all of these, but I think you get the idea. Just take the function value at the midpoint of each of the subintervals, and that's going to be the height of the rectangle. Okay, now in this example, we're going to do rectangles that would give us an upper sum on graph A, but a lower sum on graph B. And you will notice that the function is pretty similar, and we're just trying to give a representation. So remember, when you talk about upper sum or lower sum, you're looking at the y values to determine the height. So in graph A, I want you to go ahead and draw upper sums, and on graph B, go ahead and draw the lower sums, the lower rectangles, and then come back and check. All right, so that's what the graphs would look like for A. You should have every single rectangle should pretty much be above the function, and for part B, every rectangle should be below the function. So that's what the graphs should look like. If you take a look, I originally said it doesn't matter where we put the partitions in, and the idea is, how could we get more and more accurate? And the answer to this is, if we make more and more and more rectangles, what would happen to the widths at each of those rectangles? And the answer is, the widths would go towards 0. Okay, so if we take the limit of each of those sums and shrink down the width of each of the rectangles towards 0, if those limits become equal to one another, then we say that the function is integrable. And integrable just means that you can find the area under the curve. Okay, so the common limit of the sum is considered to be the definite integral of the function. And all that means, if you think back to when we were talking about slopes, slopes were limits. If the slope from the left matched the slope from the right, then that was the slope at the point. We're going to talk about the same thing here. If an upper limit overestimates and a lower limit underestimates, then if you make the widths of those guys go closer and closer to 0, meaning you're getting more and more rectangles, if those limits become the same, then that means that that's what the area is. Okay, so regardless of what kind of Riemann sum we use, whether it's a lower, using all the low y values, whether it's an upper, using all the upper y values, or just any Riemann sum like we did at the very beginning of this lesson, picking a random x coordinate and choosing that y value. As you make more and more rectangles and the widths all go to 0, those limits will all equal one another. And this is where our lovely integral symbol comes into play. Okay, so the integral of f of x with respect to x, so you got to be talking about which variable, this is in terms of, over the interval from a to b. This is called the definite integral, and this is what we're going to be studying all of second semester. Okay, a couple of important keywords or vocab words that you should either highlight or do something different with, or I don't know, some way that you can remember this stuff. A and B are called the bounds of the definite integral. Okay, so your lower bound right here, your A value, that's on the left-hand side typically. B is typically the right-hand endpoint. dx is telling you which variable you are integrating with respect to, and f of x is considered the integrand. All of these will be on your quiz. I will be testing you for your knowledge of the vocabulary because you can't do the problems unless you understand what the vocabulary means. Okay? So let's go ahead and take a look at the last page. All right, the example problem for this next one, now we're actually going to put some numbers to it. It says estimate the definite integral from of the function x cubed in terms of x from x equals 2 until x equals 3. At this point, we're going to highlight the word estimating, okay, because this is not going to be exact. We're going to be using an upper Riemann with 4 subintervals, and we're going to use a midpoint Riemann with 4 subintervals to estimate this. So the first thing that I'm going to do, and we'll go ahead and use calculators for this. I'm not going to check how well you can multiply numbers and cube them in your head right now. We'll get to that later, but for right now, it's just the idea. We're going to talk about U4 is going to equal. Now, if you're a visual person and you remember what the graph of x cubed looks like, it's something like this, and we're going to be going from 2 until 6 for the x values. Now, because this function is what we call monotonic from 2 to 6, that's a word you got to know, monotonic. Monotonic means strictly increasing on an interval or strictly decreasing, but mono means 1. So it's only doing one thing on the interval, okay? So this thing is monotonic, increasing from 2 to 6. And because of that, the upper sum is always going to be at the right endpoint of each subinterval. And for this particular example, since we are asked to use 4 subintervals, we're just going to break it up evenly. And we'll go from 2 to 3, from 3 to 4, from 4 to 5, and from 5 to 6. So the upper y value is going to happen at the right endpoint of every subinterval. So U sub 4, you know, this is the Riemann notation. It would be f of c sub k, whatever the y value in each of the subinterval is, and all of our delta x values. Okay. For simplicity's sake, again, we're going to use identical widths. So the widths are all going to be a value of 1 for this problem. So I'm going to circle this and say that this is going to equal 1. And all this says is to sum up all of your y values. So I'm actually going to do a little flip-flop here and say delta x sub k times f of c k. And again, we can do that because we're going to use the exact same widths for all of these. Otherwise, I wouldn't be able to pull it outside of the summation symbol. So our delta x sub k is 1. And when it says to sum up all the y values, again, we're using all the right endpoints of each subinterval. So we're going to use f of 3 and f of 4 and f of 5 and f of 6. And if you do all of those function values and you add them all up, you're going to get a total of 432 for the area, for the definite integral estimate. Okay, so from 2 to 6, under the curve of x cubed, okay, so from 2 to 6, you're getting an estimation of that area to be 432 using an upper Riemann sum. For the midpoint Riemann sum, using 4 subintervals, again, our delta x, our width is still going to be 1 for each of the subintervals. And we're going to go from 2 to 3, 3 to 4, 4 to 5, and 5 to 6. So that's still going to be 1. And if we want to add up all of our y values, now remember the midpoint doesn't depend on the y value. The midpoint is asking you to take the midpoint of each of the subintervals. So we're going to use f of 2.5. That's the midpoint of the first subinterval. We're going to use f of 3.5. There's the second subinterval midpoint. And get the idea. F of 4.5 and f of 5.5. If you find all of those on your calculator and you total them up, you are going to get an approximate area of 316. So significantly lower than our upper estimate. Okay, but both of those are approximations for the definite integral. Okay, so again, it was very important to notice the word estimate here. That allowed us to use the midpoint and the upper Riemann sums. And that's it for Riemann sums, and we're going to practice a lot more tomorrow, so have a good one. Bye.